Testing. Yes. So hi everyone. Thank you for coming. Thank you for coming for this tutorial today. Tutorial workshop for deep learning week. And today I will be talking about introduction to reinforcement learning because I believe that is one of the problem statements that you have to do for unit choose. And this will be a brief introduction, but it is intuition based. So I will not be going too deep to the math, but it is very important to really understand how this math means, what this math actually means in our context. Reinforcement learning. Okay, let's get started. So first, I would like you to scan the QR code to get the accompanying Google Classroom book so that you can follow along with this one toy example that helps you to understand reinforcement learning. And I think both the slides and the notebook will be shared later on in the main common chat. I think. Yes, so that you can revise and let's start. So first, reinforcement learning. Why do we need reinforcement learning, and what is the agenda for today? So first, we would try to visualize what is reinforcement learning. Have a big graphical picture. Then we will go down to the Markov property and the idea of utility. So it sounds very scary, but they are the integral part of reinforcement learning. Then we will also explore the Bellman equation, which facilitate the solving of reinforcement learning problem. Then we will proceed on how to solve this problem. So there are two ways, but you can see that the solving the solution is in quotes. Why is that so? It is because we are not actually, completely solved at the optimal point. Unlike your equations, unlike many of the analytical equation that you have, but we are trying to do in like exploration and a numerical approach in order to solve this problem up to the point that we find satisfactory. Yeah, and the diagram in this slide represent one of the common idea or the big picture idea of what reinforcement learning is. And if you continue to read up or learn about reinforcement learning, research on them, this diagram keeps coming back and back because that is the main idea. But for a normal person who just approach reinforcement learning, the diagram is quite big picture and you don't really understand or appreciate what it is saying. So let's dive right in. So what is the difference between like machine learning as your standard machine learning and the idea of reinforcement learning? So if you have heard of machine learning and then attracted to deep learning because this is deep learning week, you might have heard of the idea of machine learning and vaguely understand how they work. So the machine learning model take in an input. This input will then be processed by a model. So this model is trainable and the model will provide a relevant output. What is the relevant output? So for example, in the slides, there is photos of people. So that is our input. Then we put it into our model, object detection model. Then what are the relevant outputs? So first we have to detect the person, and then we have to give a bounding box, right? Give a bounding box around that person and classify the person, whether is it a person or like a building or a stop sign. So those are the relevant output. And these models can be equation, statistical model, or deep neural network. So what is the difference? So equation can just be, your Newton law of parabola equation. So technically it is kind of a model, but we don't use that in machine learning because machine learning requires a lot of training data. So we can have like statistical model like your SVM, your tree, what do you call that? A binary tree and regression model, those kind of simple statistical model, or you can do the deep neural network way. It requires a lot of training data. So that is why there is a term learning in the name, because it is not just an analytical equation, but it needs data to make sense of the pattern. Similarly, for reinforcement learning, we also need a lot of training data, but this training data doesn't come from a very, a package of data that is some elsewhere. So for example, the object detection, we can just pull down the data set from somewhere, and or you can just straight away randomly take pictures and start labeling. But for reinforcement learning, the training data comes from the agent interacting with the environment, right? So the input, so how does the whole process flow works? I think I have the, where I have the, okay. Laser pointer. Yeah, laser pointer. Okay. Yes. So the agent has to interact with the environment and taking the input from the environment. So this can be a car taking in the sensor, right? And I just want to foreshadowing that the idea of this input is this S stands for state. So the state can both represent the current state of the environment and what the agent gets. Sometimes, so as you learn more about reinforcement learning, these concepts start to get blurry and there are edge cases. But for the sake of simplicity, our input is the state. But as you go, you will know that, okay, sometimes when the world start progressing or like the world start changing, the environment start changing, the agent might only see a part of it, right? For example, now at the moment, I can see what is happening in this auditorium, but I cannot see what is happening in Paris, for example. People taking photos with the Eiffel Tower, I don't know that. Yeah, because I cannot observe. So as you go along, there are state that is in the environment, but the agent cannot observe. But the same idea, the agent has to take some input from the environment, and the environment is highlighted because it is important. Without the environment, then we cannot really have a reinforcement learning problem. In machine learning, right, you just need a model, and then all your input data come from a pile of images somewhere some people have collected. But here you need both the agent and the environment. So inside the agent, there will be a model that gives out a certain policy, right? And this policy defines how the agent will take action in the environment. And as the agent take action in the environment, the agent will change its states within the environment. And the environment itself can also continue to change the states. It might sound a bit convoluted, but the idea is that the environment can keep changing and the agent has to navigate in this environment, unlike machine learning. And what is this model? Usually we write equations or we use English description to describe model, but what are they? Like how do we physically represent them? So models can be lookup table, just a simple lookup table, a simple array, a list, or it can be like deep neural network. So you can see that deep neural network is simply a tool to solve problems. Deep neural network can be used in machine learning and in reinforcement learning, right? So deep neural network is not fully reserved for machine learning or reinforcement learning. And actually, when you use deep neural network to do reinforcement learning, then they will call it deep reinforcement learning, DRL. So our event is Deep Learning Week. So I guess deep reinforcement learning also, it is a deep type of learning. Yes. Okay. So the key ideas, state, action, reward. The agent interact with the environment by taking action. The environment will transition the agent to a new state and give out a certain reward. And then we will take a look at utility and expected utility as well as Bellman equation. So what is the final objective? The main objective is to maximize the reward received, the cumulative reward. So as you move inside the environment, you can incur negative reward or you get positive reward. The idea is that we can define a starting point and the end point. And we ask ourselves, how do we go around, how do we operate in the environment to maximize our reward? Yeah, from start to end goal. So usually in order to describe this, we use this idea called Markov decision process. Why is this Markov person here? Because he first start the idea of the modeling the process as different as a graph, right? As a graph. and then there is the state, and then it takes action. So you see that there are like various visualization of the same reinforcement learning problem, because different visualization give you a different perspective on the problem. For example, here, so this on the right down here is a grid like shape structure, right? So this will be the problem that we'll be tackling in the Google Colab notebook. So what does it mean? So we have a starting point here and we have an end goal. Our aim is to go from the start to the goal. So this grid square gives us a more natural way of looking at the problem, right? Because we know that our world is a grid, and then we have to traverse inside the grid. But sometimes there are various things that we don't really get from this grid, which is, okay, I am, for example, if I'm here, what is the probability of me just, slip and fall down the cliff? We don't know that. So therefore, we also use this representation, which is a graph. And if you are from CS, you will have your digital logic. If you're from Triple E, you have your digital electronics, I believe. I hope you are year 2 or have learned this, because when you do state machines, right? When you do state machines, you have encountered something like this. You are in a certain state, and then you have to transition to a different state. But in your digital logic, when you transition, it is 100% chance, right? You decide where you want to transition. But in the Markov decision process, in this environment, as the agent navigate in this environment, there can be different probability, right? It can, from state S0, it can take action A1 to go to state 2. But it can also take action A0 and then go back to itself. So even though the agent wants to take a certain action, there is a probability connected to that action. Sometimes we might not go to the state that we want. So now you can see that you can start seeing how the problem can be quite complex, right? The agent doesn't go in the direction that it wants, but there can be changes in the environment that force it to do bad things. So just to recap, there is a state, which is, we usually use the S term. There's an action where the agent wants to go, what the agent wants to do. There is this transition model. So P stands for probability, right? The probability of going to state S, comma, SS prime, which is the next state. If I take action A at state S, and then there's a reward function at state S, and then there's a policy. So a policy is just map a state to an action. Again, it is still very math heavy, and we might not know, okay, what are these symbolizes, or what do they represent? Let's follow along. So I first want to tackle this idea of Markov property and utility first, because they are the core assumption of reinforcement learning. So Markov property is the idea of that there is no history of the previous state. So whatever you find yourself, whatever the agent find itself at, which is the current state, is that it has to decide from there. It doesn't have the history of what it has been before, right? So if you reach the same state, you will see the same set of action, same set of transition probability. So just to visualize it, or like just to make a simple or fun connection with our daily life. When we reach university, right, we have the options to do either CS or Triple E, let's say. I think there are other people from other major as well, but let's use this as 2 examples. So either CS or Triple E. Then you spend 4 years in, let's say, Triple E, because I'm from Triple E. I spent 4 years in Triple E. Then you ask me a question. If you are to redo a university, what would you choose? So inherent in that question is the idea that you can bring your 4-year experience back in time to redo or to re-evaluate your choice, right? So that is the assumption of that question. But in Markov decision chain, in the Markov property reinforcement learning, the moment you go back to this state of deciding the major, you don't have any memory at all. So 4 years of Triple E down the drain. So I have to decide again. Do I go to CS or Triple E? So the question is, okay, so how do I make a decision? if I don't have any memory of what I've done, how do I even solve the problem, right? How do I even navigate in this environment? And you also said, okay, I thought the agent is supposed to go through this environment a lot of times, right? So if it goes through it a lot of time, shouldn't it have some memory? So the idea is it doesn't keep track of the memory. The memory is not stored in some array, but the memory is stored as the quality, the utility of that state. What does that mean? Next slide. So the utility encapsulates the desirability towards a goal. So you have to identify a goal, like you have the environment, you have the agent, and you have a certain goal that you want to achieve. You want the agent to beat the game of chess, for example. You want it to solve some UN problem, like UN sustainability goal problem. You want the agent to learn that way, but you don't really know how. You just want the agent to go out and learn because you yourself also don't know how to solve that problem. So there is a goal. There is a goal, and using that goal, you can define your reward. But reward alone is not enough, right? Reward can be attached to a certain state, but it is not enough. Because let's say if you're going to Apple, that is a good one. So you get a good reward when you go to Apple. But how does that help me back when I'm all the way back here? Because I still need to decide whether I do CS or Triple E. And the agent can only observe the next state, that is next state. So if the agent is at state number 1, the maximum that it can see is what is right adjacent to it, which is S2 and S3. It cannot see whatever in the middle. So how does it progress toward the goal? So we need this idea of a utility. So back to the university question again. So what is the potential utility score that I can use, which is expected salary? And this ties back to our goal, right? If your goal is to get money, then your expected salary will be your utility. If your goal is to do something else, then your utility will be different, right? So if your goal is to get, I don't know, what else? Yeah, if your goal is to know art, then probably CS and Triple E are not the best choice. So the utility are a different one. So that is the idea of Markov property and the idea of utility. So they are kind of like sandwich our agent. What do you mean? What do I mean by sandwich? It's like, so the agent finds itself in a certain state. The Markov property said that you don't remember anything from the previous time. But the utility tells you what to do next because it encapsulates the desirability towards the goal. So even though you don't know how you might evolve, like, so after you go to CS, whether you go to a bank or a FANG company, you still don't know. You still don't know where you end up. Probably when you go CS, then you say, crap, I don't want CS anymore. I go and open a coffee shop. You don't know that, right? The only thing that you know is if I go CS, I will have a better chance of getting my money. So the future is also unknown. The past is unknown. The only thing that signals the agent to do things is the utility. So there is this idea of expected utility. Back to my first idea of the different state, right? When you transition from one state to another, there is a probability because you cannot always get what you want. So in statistics, when we deal with expectation, it just means an average, a mean. And if you recall your statistics, then there are various possibilities, and each possibility has its own probability. Okay, sorry. There are various options, and different option has different probabilities. And the expected value is you just multiply the probability with the value, right? So if I take action A1 and then 20% of the time I will have 20 points, and 80% of the time I will have 10 points, my expected utility will adds up into 12, right? Because you multiply the probability and the score, get 12. So why do we think of the idea of utility as a distribution to get the expected value? Yeah, same idea. Because sometimes we don't always get what we want. The agent wants to do a certain action, but will not always get the same action. Sometimes it is non-deterministic. It is a probabilistic action. And why do I put this game image here is when you play games, right? Sometimes you get a critical hit, but you don't really know when you get the critical hit. It's just by chance. So yeah, this is the idea. Like we as an agent, we want to attack a character, and normally we would expect an average damage of, let's say, 1,000, but sometimes we just get lucky and get 2,000 damage. So that is why we need this idea of expected utility, right? Because it is the utility exists on a distribution. We want to get the expected values. So, and then this is why we can aggregate our experience. So like we said, the agent play around in the environment, but it doesn't have the memory. So how does it know what to do next in the next round? It is by using this expected utility, right? As it do more and more and more of something, then it will average out all those runs and see what action is more desirable. So just to do some math to familiarize yourself with this idea. So if I'm here, I'm in state S1, I can take two actions, A1 or A2. And then in each action, I can get two different state altogether. So the question is, okay, what action do I choose? So the expected utility of the action A1 is, yeah, you multiply this, add up 30. A2, you multiply this, add up 50. So 30 and 50, probably A2 is the better choice. So if you are being greedy, right, you want to take the best action, you just, from S1, the agent will take A2. Yeah. And similarly, if the action is also probabilistic, then you can say that, okay, when I'm at state S1, the state S1 has a utility of 46 because I also average out the two actions that I can take in this S1. So probabilistic action. Yeah. So this is the tree that you just progressively multiply out. But this idea, I bring this up to show you an intuition of how let's say how the utility is being like calculated. But you are not the person calculating. So don't worry. As long as you understand the big picture, let's move on. Right? So there's another idea behind the utility. Yes, we can condense all of the desirability into one single score, but that single score might not be the same all the time. If I tell you I will be giving you $100 right now, would you rather it, or would you rather to take it now or 1 year later? Right? It is $100. So after 1 year, there will be depreciation. I might graduate and then we will not see you again. So the thing in the future is very uncertain, but you would rather take it now. So therefore, we have this gamma term. So the gamma is trying to discount future rewards, future utility. Yes, you can have a utility in the future, but because it is so far away, you will need to discount that. Yeah, don't be afraid of this equation. Just understand the significance of the term gamma. And usually in the reinforcement learning problem, this is around like 0.99, actually quite large. The gamma is actually quite large. The gamma is actually quite large, even though we can vary it from 0 to 1. Usually it is more close to 1 than average. Yeah. Okay, so this is the very, very complex, the Bellman equation. Yes, we might be intimidated by it, but let's break down step by step. So first we have the current state utility. So back to that idea, right? Each state has a certain utility. This utility informs us whether the state is desirable towards our goal or not. And then we can calculate that by adding the reward. Then this is your discount coefficient. This is your expected utility of the next state. So S prime is the next state. So you are at state S, right? Let's say you are at here. And then what is S prime? S prime can be from S2, 3, 4, 5. Yeah, these are like all your adjacent states. And then we can sum them up with the probability. And then if we are like taking the maximum, the greedy action, right? Then we can propagate the utility from S3, S4, S5. We can, yeah, do that calculation to propagate the value to S1. So that is how the idea of reinforcement learning is being used. So as you experience the environment more and more, you will know what are these values and how they are related to each other. Yeah. So main idea, yeah. So the main idea is that you can propagate the utility at state S prime to state S, which is your current state. Yeah, so you propagate the score. And why do you take the maximum? I think, yeah, because you want to take the maximum action. So this is the key equation, but the key equation can change. So that is the job of the researcher. Reinforcement learning is still an active research field. But I put it here just for you to get the taste of what it is, right? Get some representation and break it down, try to break it down. Okay, so now the question is, okay, so what is the difference between a reward and a utility then? What is the difference? The difference between the reward and the utility is that the reward will be given out to you when you arrive at a certain state. But the utility encapsulates all of the information from the current state to the goal. Where is the reward? Yeah, so here, let's say in the cliff problem, when we define the reward, we will say that, yeah, let's use this as it, because it is bigger. So here in this grid world, we have the cliff and we want to stay away from the cliff. So the way we define the reward is that when we are in the cliff, when we fall off the cliff, we will get -100 reward. And then for the next step, we will have to go back to the starting point again, right? If we fall down the cliff, we have to go back. And if we don't fall down the cliff, then each of the square, we will incur 1, -1, -1, -1, -1. So each of these is -1. So what is the difference between the reward and the utility? So the idea is that if I have, yeah, so for the reward, each of the square will be -1, -1, -1, -1. So the moment you land on the square, you get -1. The moment you land on the cliff, you get -100. So that is quite clear, right? But the idea of the utility is that, let's say I'm here, I'm at this current state. Then I look left, look right, look to various directions, and then I see that this is, the utility is 50, -50. The utility down here is like -80. So without knowing the world, maybe I don't know the world is even a square. I don't even know the world has a cliff. But at this current state, I look left, I look down, I see two states. One state has a utility of -50, and the other state is -80. I know that if I'm to be greedy, right, and if I want to reach the goal, I should probably go here, right? So the utility, you encapsulate all of the things, like all of the, encapsulate the desirability towards G. Okay, so let me try another time, try again, or use another intuition. So we know that the agent can explore, right? The agent can explore in this world, like in various ways. I don't know whatever it does. And we don't have the knowledge of the past. So this -50 sum up all of the possible pathway to G, right? And what it is saying is that, okay, because I have explored this area a lot, I know that when I'm here, going right will tend towards the goal better than going down. Yeah, so this is why all of this trajectory down here will be propagated using this equation. Yeah. So how does that? So let's do one time. So if you have the U down here, and you have, so this is the next state. This is the next state. And then this is a current state. What it will look like is that at the goal, when I am at the goal, I will, the whole run is done. Right? the whole run is done, I will not get more negative reward. So from the goal, I can like propagate the utility backward. So for probably here, down here, the utility is like -2. Down here, the utility is -3, -3, -4, -5, for example, right? This is -6. So if I'm here, I go to the -6, then I can see this -4. So by propagating the value, the utility back, I can start to know where I should go next, right? So that is the general idea. Yeah, erase, yeah, all. Yes, so the reward is defined at different square, but the utility is also defined at different square, but they represent different things. They represent the cumulative desirability towards the goal. So the big picture of a training step is that, so this is the progression of your training time. But during that training time, you will be going through the system a lot of time, different, multiple runs, multiple trajectory, from the start to the end condition. And remember, the end condition doesn't mean it is a goal. The end condition just means that you end the run. So for example, in this case, if you go around and then you fall the cliff, that is an end condition. You have to go back to the starting point, right? So that is the end condition, the termination condition. And by falling down the cliff, you incur a lot of losses. But ultimately, you would want to go from starting goal to from S to G. And usually going from S to G straight away will give you the minimum cost. So far, do you have any question? So that is the intuition. So the intuition is the agent will interact with the environment, and then the environment will give the agent the reward. And as the agent goes through and through the environment multiple times, it can then update an internal utility score of the environment. Right? It doesn't remember what it has done. It doesn't remember the trajectory. It just remember the utility of a certain state. So one way to solve this problem is the idea of greedy policy. So value iteration. What does value iteration mean? So iteration is going through the environment multiple times, and value. So now you can see that there is like quite a confusing mismatch of terms. Even though it is called value, we can also think of the idea of value is the same as utility. So basically, value iteration means that as we go through the trajectory, go through the various episodes in the environment, we will get a better idea of our utility score, of our value. And the policy that we are using will be a greedy one. A greedy just means what is nearby me, I will take the best possible action. Sometimes the greedy policy is not the best, but this is one of the way to do it. So you can see that there are two ideas starting to affecting the agent decision already. One is the value, the utility, and the other is the inherent policy. In this one, we use greedy policy. So we only care about value iteration. So that's why we can evaluate the utility of all the states and pick the state with the highest utility. So you can see in this diagram, so after one iteration, so this is the initial, let's look at the environment as an initial state, right? At the start, there's no reward. So green and red are the reward. Green and red are the final, the ultimate reward. But the rest is, there's zero rewards whatsoever. So how do we know if going up or going right is the correct one? You don't know. You just let the agent run around and see how. Then after 5 iterations, using that Bellman equation, then you can propagate the idea, right? You propagate the utility being in a certain state back. So when you start at 0, 0, you look up, you look right, then probably looking up is 0.27, which is better 0.22. So you take an upward motion. So why does it come down to 0.27 and down here is 0.22? Because if you go down, you have a higher chance of slipping down this negative one. Whereas if you go the upper route, then it will reach the final destination without slipping anyway. So yeah, you can see how even though we don't really know if there is a negative reward region down here, but this score is propagated back, and comparatively 0.222 is less than 0.27. Yeah, so this again reinforced the idea of you don't really know the future, you don't really know the past, but you have the utility score to guide your decision. But another one will be policy iteration. So again, there is a policy and then there is a value. We might sometimes think that, wait, if you have the utility, then isn't that the sure way to win, right? You just follow the best utility. But that best utility might not always be the correct path. Yeah, for example, if someone show up and tell you, okay, you want to sell drugs, then probably if you sell drugs, you get big, massive amount of utility of money. But you know that in Singapore, die very quickly. So yes, always going for the maximum utility is not the best. So there is, we can separate a different policy. And when we observe different state, yeah, the agent will give a different action. So when people say the agent and the policy, we can encapsulate the, oh, that's it. Yeah, we can think of the agent, different agents who have different policy, different ways of taking action. So how do we do this policy iteration? So we started out with some estimation. We don't, because we have not experienced the world, we start out with some estimation of our value or utility. Then we will evaluate the current policy. So for example, if the current policy is keep going up or going right, then after going 1, 2, 3 multiple times, it will evaluate whether the score is high or not. And then it will start to adjust the policy to see if it performs better or not. Then after adjusting, it will then evaluate the new policy. So VPI is evaluating the current policy. Then after you evaluate, you change the policy. Then you evaluate again, and you change, and you evaluate, and you change. Then hopefully you will reach an optimal position, right? An optimal V star is optimal value, and high star is optimal policy. So again, one question, okay, that's a lot of math, that is cool and all, but what are they? How are they physically represented? So it can be a lookup table, it can be a function, it can be a mapping or a neural network. The idea is it maps a state to an action. So that is the idea of mathematical function, right? It maps something to something, x to y. And what does the function calculate? It depends on you, depends on the problem at hand. And if you want to make it complex, then you use neural network. And yeah, this slide will reiterate, right? Reiterate the idea. And this equation is the equation that tries to represent how the policy can be updated. So basically, yeah, we try a lot of policy, we try multiple type of policy, see which one give us the most utility or the most reward at the end. Then we update the policy accordingly. So if this is your neural network, I hope you have some familiarity with neural network, then you can use your gradient descent, right? Gradient descent is kind of like, okay, I wiggle this weight a bit, see if the value that I get at the end improve or not. Then I will progressively change my behavior. But if you are doing, let's say, this grid work, because if you have the grid work, you have a clear transition state. You can use, in CS, people use dynamic programming, or just lookup table, store everything in the lookup table, and then just keep propagating the idea back to the starting point. So what is difficult? The difficult thing is that the lookup table is not scalable. The lookup table is not very useful when the world starts to be more complex and more complicated. So how do we solve reinforcement learning in higher dimension? So that is where the deep neural network comes in. So we use deep neural network to predict the utility. We can also use the neural network to represent our policy and use the gradient descent to update both. And that will be in the next practical session. But in this photo, I'm like representing what is so difficult about that. So if you recall your grid work, you can define a grid, a play area of, let's say, 10 by 10, no problem. You can do a lot of things. But here, the input is a screenshot of the Atari games, right? And the screenshot of Atari game, probably it will be bounded by 100 by 100 pixels, but the values of those pixels can vary widely, right? The pad can be down here, the pad can be up here, the score can be 2 or like 100. Basically, even though the resolution is 100 by 100, the values in those squares can change drastically. So the dimension is very high. So how do we do that then? Then that is where we have to do the deep neural network idea. We have to use deep neural network. But that is the problem for tomorrow, because tomorrow there will be another session on the practical side. But then I think if you are interested, if you are choosing reinforcement learning as the problem statement, I also encourage you to, let's say, read up and see if this is applicable to your use case. And just to reiterate, so I think the people showing up here are the people wanting to do reinforcement learning, right? So this is not insider knowledge or anything, but I will want to like stress the difference, right? So in machine learning, you have one component. Oh, wait. Oh, I think I skipped this. Okay, this is very important. Yeah, this is very important. I didn't go to this slide earlier. So how to visualize this? So in machine learning training, right, you have the model, but the model is one part of that. You have your model, your architecture, whatever architecture that you come up with. So you put in your input, you predict, then you compare, which is a loss function, you compare against your label, then you do the back propagation to update the weights, right? So this is the training pipeline. Then when you want to do prediction, you want to do inferences, you take out the model and then just pass one time. Input, model, get the prediction. When the model is good enough, then this alone will be enough. But for reinforcement learning, DQN stands for Deep Q Network, right? Because there are various ways to approach deep reinforcement learning. But as a comparison to machine learning, you can see that the structure will change quite drastically. So now the input will be your state, your reward, your action, and then whatever like next state that you want to go towards. And then you have your model. So here, because it is we are only evaluating the utility, right? So we assume that it is a greedy policy. So what is the output then? The output will be first a utility and action. So this model is actually from the utility, it can already take action already. So after it takes action, the action goes to the environment. The environment will evolve into something else, right? The environment will respond to your action. Then it will give you back a new state, say ST+1. And then the whole thing go round and round again. Right? So as you go through the environment, this is what you have. You predict, you take action, the action goes to a different state and pipe back into the input. So meanwhile, you want to predict that utility. You want to predict the utility score. So what do you do then? Then you put the utility in and compare it against the expected utility. Actually, the Bellman equation, right? We use the Bellman equation. Then you compare it against that to back propagate, to update your Q network. So this is another component. It's very different from machine learning, right? And for inference, yeah, you take out You take out the back propagation and the Bellman, you just have the model will calculate utility, the model will take action, the action will affect the environment, and go on and go on and go on in the loop. Yes, so you can see that there are one additional components to this diagram. So if you do your statement 1 or statement 2, statement 1, I think it is about the cleaning up the data, but the cleaning up the data can also be formulated as there's an input and there's an output, and then that is all. For like generative AI or normal machine learning tasks, you have your input and then you output something. But for reinforcement learning, there is a model and then there is an environment, right? There is an environment. So where do you get this environment? Probably you have to code it out. Like if you want to tackle a certain problem, you need the environment. The environment is not given to you. It can be a simulator, it can be a simple grid world simulation, it can be whatever. There are benchmark environments that people use to test reinforcement learning algorithms, but those benchmarks are not really aligned with our problem statement, isn't it? I think I will be introducing in the next section, but the idea is, so yeah, gym, there is this idea of an open AI gym. So this is one of the ways that you can standardize the definition of the environment. So you see in this environment, it is trying to land a spacecraft, right? But based on the problem statement, you're not really like landing any spacecraft. Right? So if you try to develop your algorithm using this environment, it doesn't really make sense. And we are also not testing you on developing a new reinforcement learning. This is a hackathon. We're not asking you for a research quality proposal of a new architecture. No, we want to ask you to use this idea. You understand reinforcement learning, then use this idea of reinforcement learning in a graceful or creative way to solve some problem, right? Yes. So there are two main components. There's a model and then there's an environment. And it is up to you to be creative in either the model or the environment. Yeah, so I think this is an important point. Be creative, but choose your battle, where to be creative. So with that, I think we will be transitioning towards the Google Colab. Yeah. So if you have your Google Colab, so this is the grid work problem. So let's go one by one. So you see, this is actually, it is not this environment and the agent is not formulated. Can you clearly see? Do I need to be bigger or anything? I think around here is fine. Yeah. So this is a grid world, relatively simple. Nothing is moving in the world, and there's only one agent. The agent goes from start to the goal, and there's a cliff. The objective is to avoid the cliff as much as possible because it will incur losses, right? So the first question is, yes, you need to define your environment. You need to know what your agent can do. Go up, go down, or manipulate something in the environment. And then how the environment change based on the action. And then you will then define the reward, because ultimately the reward will signify what you want the agent to do, right? You want the agent to go from left to right. Yeah, you want the agent to go from start to goal without falling down a cliff. Then you want to punish the reward by minus 100. Then you might ask, okay, so why is it that I also have negative reward as I take steps? So the idea is that if you are just walking around, like you're just like going in a circle without reaching the goal, we also don't want that. We want you to rush you to the goal. So every additional step or like every unnecessary step that you take is a punishment. So there is like a small reward punished at every turn. And then there is a big reward when you fall down a cliff. So I think this is also important as well. In reinforcement learning research or reinforcement learning problem, people will, I can go back to this. Yeah, people will look into this idea, right? So what is your state? What is your action? What is your reward? Because reinforcement learning can be formulated in a very predictable way. So what we will be focusing on is, yeah, how do you define your state, action, and reward? And what the agent will learn and what is the policy. But that is something that it will evolve over time and we cannot predict. What you can design are the action, state, and reward. That is what you can design. Okay, that is a lot of starting point. Let's dive right in. So here we only have like a few simple library, NumPy to get a random and then plotting things. So what you can do is, yeah, you can do file, copy to drive, then you can play around with your own. Because if you are trying to manipulate here, then I think you can run, but you cannot edit or save it. Right, so I will try to run. So let's see. So first, I will see if it, yeah, so this is the how it will look like as it move around the world. And then at the end, I think it will spit out a graph. Yeah, it should, but then I will just run again, run on. Okay, so how do we start even to define this world? So you can look at here. So we have height, width, which are the variables. So it is a 48 cell world. There are 4 number of action, and the action can be left, right. If I define X as the first one, and then Y is the second term, then you can do go up, sorry, left, no, +1. +1 is go right, then go left, then go up, then go down. Yeah, probably like that. So the starting point is 0, 0, and then the goal is 0. Okay. So I'm sorry. Here, somehow people define it like X is going up and Y is going right. Yeah. So again, it's all based on your definition, right? 0, 0, you start at 0, 0, and you end at 0, 11. So 0, 0 is the S, and 0, 11 is your G. 0, 0, 0, 11. It's all based on your definition. Then we want the agent to explore like 500 times, like in the episode. So then this gamma, alpha, epsilon. So what are these alpha, gamma, epsilon? So there is this no discount. So when we put gamma is 1, there's no discount of the utility. Just now I introduced the idea of the discounted utility. Then here, just to simplify the problem, no discount. Alpha is 0.1. So this alpha acts as the learning rate. If you know about machine learning, then there is a learning rate, which can tell your models whether to update very fast or not. So learning rate. So number of runs. So what does it mean to have a run even? So runs is like you do 500 episodes 10 times. So this is just to average out, like smooth out the curve. Because sometimes as it explores, sometimes it will get a very negative reward. So usually people will do like a lot of times to just average out the number. And that is also inherent in reinforcement learning research as well. Everything is probabilistic. And if you appreciate that term, right, probabilistic, it means that probably you cannot replicate the result. But the idea is after you have done it enough, it should, tend toward like the mean. Therefore, running one time doesn't show you anything. Sometimes there can be outliers. Therefore, we have to run it multiple times to really validate what we're doing. So here are some. So R is reward. Sum is, the accumulated reward. Number of zeros, then there are runs. So this is a three-axis matrix, right? There's a number of runs, there are a number of episodes, and two. So why are there two? Because we are exploring 2 different algorithms. There's this SASA, and then there's Q-learning. I think I will not be going through the SASA and Q-learning here. Right. There's also the idea of, I will also put here, temporal difference. Yeah, so if you want to take a look, you can take a look, because next time tomorrow we'll be doing the deep Q learning. So these are a more standard, the standard approach in the grid world. Yeah, but they are quite important. Tomorrow I'll be going through this. So run in range number of runs, run this 10 times, and we run it 2 times, and then we run it like 500 times, do various episodes. So you can see, okay, so this Q table here, so Q table, number of zeros, height, width, and number of action. So this is height, width, and number of action. So this is your utility lookup table, your value or utility lookup table. So what does it do? It will, each state, so what are the states? The states are the coordinates. You have your height and then you have your width. And at each state, there are 4 possible actions, so different number of actions. And what are we trying to do? We are trying to calculate the utility, right? And we have to store it somewhere. So this storing is not really about the memory, right? We're not really storing memories of our previous trajectory, but we're storing the utility, the desirability towards the goal. So yeah, here it is a simple lookup table. NumPy 0, so array at the start is all 0, height, width, and number of action. So we start at a starting point, and while it is not the goal, then we will randomly explore, right? We will randomly explore. So here, the policy. So this is one of the policy that we're telling the agent. What is the policy? The policy is you can be greedy, but you are greedy 0.1% of the time. So epsilon 0, epsilon random exploration. Yeah. So this is how you parameterize policy as well. It can be greedy 90% of the time. Then the next 10% is just to randomly explore. And then this is also important in reinforcement learning, because if you are greedy straight away, then you might fall into like local optimal points and you cannot get out, right? Sometimes you go to university and then you think, oh, CS is so cool, right? Like CS has so much money, and then you just go ahead and do CS, but you're not like taking into account the general trend of the world. Nowadays, like Nvidia stock is like pumping already. So triple E, let's go, right? Not CS, probably. So yeah, exploration is important as well. So this is one of the way that you can parameterize or write down what is the policy. So number random, if you do the random and it is fall below 0.1, then take random action, right? Random range, take random action. Else, right? You see else, you take the maximum of the Q table at that state. So ST is the current state. Then double dot here is that, out of the 4 possible action, take the argmax. Then after you take the argmax, then you evolve to the next step. You transition to the next step. So next step is NumPy add. So state S, action T1. And toolist, NumPy array toolist. Yeah, so it will add here, and then it will turn that back into an array, and then it will turn back into a list. Why did I write this? Just because of the the addition, right? Because initially I put this as a list, right? And when we add 2 lists together, they don't do. So if I add 0, 0 plus 0, 11, it doesn't become 0, 11. It becomes 0, 0, 0, 11. So the operation of a list, of a Python list, and NumPy array, 2 elements are very different, right? So you can see here, it is a simple environment and a simple agent. And you can see that I'm writing a very beginner's code right here. I'm writing like, okay, if else, if else, if else. It is control code, right? Control flow, if else, if else. But if you are to do reinforcement learning properly, you should separate them out. Like there is an environment class, and in the class, there are attributes and methods. And then the environment will evolve over time. and the agent will take action based on the observation. So it is better to write this in an object-oriented way instead of this if and else. So why do I say that? Because here you can see that if next equals 0, if next one is not 0. So basically this is checking if it is a cliff or not. Right? If, what is this? If, did I miss something? If this is a cliff, yeah. So this is, if you keep doing if else, you will bump into this problem of, okay, I need to make sure that the if else order is correct. But you don't have to do that. You can just do object-oriented programming. You define a class, then you operate on that class. So if it is a cliff, minus 100 and go back to the starting point. Else, right? Else then you transition, right? You keep moving. Yeah, if you go overboard, you go back. If you go too much far right, you go back. Things like that. Okay, so now is the two different algorithms. So SASA and Q-learning. So I here is the I in range 2. So I'm doing two different modes of SASA and Q-learning. Right. So what is the difference between them? Let's first look at what it is trying to show, right? Yeah. So this is the diagram that you should have after 4 minutes of running. Just now it was showing here. Yeah, after 4 minutes of running, then you have this diagram. So in this case, it is quite sad, right? Like you don't really know if the agent is like moving in the world or not because there's no visual representation, right? You trust that your simulator runs correctly, that your logic of the environment is correct. And the only thing that you can see is whether it get a high score or not, right? And then here you can see that the two algorithms, SASA and Q-learning, one is better than the other. And what is the visual representation of this idea? Because we are doing our policy is to exploit and 10% exploration. So there is a chance that, so if we look at this, right, and we tell ourselves, okay, how do you go from start to the goal at the fastest? Probably going along the edge of the cliff is the best, right? Because it is the closest. If you go up here, you incur 1, 2, 3, 4 more negative ones. So that is probably not a good deal. But if you, yeah, so that is if you are greedy, then going the optimal path is down here. But because your action is greedy 90% of the time and explore 0.1% of the time in a random direction, right? So sometimes you're like walking, okay, I'm optimizing, and then 10% you fall off the cliff, even though you want to go right. So that is the idea of, probabilistic action. And you might say, okay, then why don't we just be all greedy? Why do we even put this 10% exploration? And like I said, exploration at the start is very important because it allows the agent to explore. So technically you can say that, okay, probably after 500 steps, you can start being greedy instead of exploring. That is also something that you can adjust as well. But this idea of exploration is also important when you start doing more bigger reinforcement learning projects, because the world is not as clean as we want. We cannot just do the thing that we want. The robot might slip, might fall. There's a sensor noise. So the exploration or like the random noise is very important to be added in. So what is the difference, right? So uniform, explore, next, next. Yeah, so if I'm exploiting, exploit just means greedy, right? Exploit is greedy. So the next action will be maximum of the Q table. I look at the Q table, what is the maximum? Then I take that. And then when I start doing the update, so these are the two important lines between the two equation. the difference between SASA and Q-learning. So I think I will highlight this idea. So this is a max, and then there's a Q table, right? There's a difference between a max Q table and then reading from Q table. So what is the idea of what is the difference behind these two? The difference is that, remember our Bellman equation. So this is how the code is writing down the Bellman equation. So what this does is, in this Bellman equation, I'm taking the max action of the next step. While over here, I'm referring to my existing table. So there are two different meanings of this update. So one is I'm trying to behave based on what I have been, based on the current utility. And the other is I would always do my maximum, right? I will take the maximum Q table of the next state. So yeah, so I think I will not be elaborating much on this because I also want to have time for questions and other things as well. But you can really look up to the SASA, read up on SASA and Q-learning. And the next session will be more on the deep neural network approach. And I will be visiting this tomorrow. But the idea is that it will give us two different graphs, right? So the one will be taking the optimal path. So this is if we are taking the maximum value of the Q table. Basically, we are trying to okay, just go to the best possible path, okay? You don't really care about anything else. So 10% of the time it falls down, and then that result in a very negative dips down here. But if you refer to your own utility table, right? You keep referring to your own utility table, then there is a more conservativeness in your behavior, because you know that, okay, 10% of the time I will be going downwards. 10% of the time maybe I will slip somewhere. So it is better to be safe and take the upper path like this, right? So episode, yeah, Q-learning, average, and then after that, after going and exploring multiple times, we are just plotting the graph and smooth out the graph, because if not, the graph will be very jagged, and then plot the diagram, right? So that is all. Yeah, exploration 1, discount 1, learning rate alpha 0, 1. So that is all for this notebook as well. So now I'm just trying to repeat the main idea, right? The main idea is that you need an agent. You have to put that down in a program, right? You have to define that in a program, in a code, and you have to define the environment. You have to write that down in a code or take some simulator online. And the suggestion is that you use object-oriented programming to make an agent class and an environment class. Make them two separate things. So that is also easier for you to program, right? And if it would be good if you can also show what the environment is doing, right? So if you are trying to formulate an environment like a grid world like this, and you are not showing the judges what is it about, then you should have a conceptual diagram, something like this, right? Over here, I cannot really print out this thing, right? So my Q table is 4 by 12 by 4, which is like a 3D cube, a 3D rectangular block. So you cannot really visualize the Q table. So at least have some visualization of what your environment and what your agent is doing. Okay, so that is one. How do you define the environment and how the conceptual idea of what is it doing? The second one will be, yeah, some sort of graph to show that, okay, it is achieving what it is supposed to do, right? Probably something like this will be beneficial, right? Because we know that, okay, based on your current definition of a reward, we, the judges, not me, okay? I'm not the judge, but that is the thing that you should do to impress the judge, because that is the idea of reinforcement learning. So you should show something of this kind of graph to show that yes, the algorithm, the agent is improving, is converging towards some meaningful value, right? If your graph is like up and down like a sine wave, then okay, this is not really a sine wave, but yeah, if there is no asymptote to your agent performance, then we will ask you, okay, what is it actually learning? So how do you get this graph? And how do you like maybe make adjustment? Then there are various parameters, right? Your gamma, your alpha, your epsilon. Sometimes you want to explore, sometimes you don't. Yeah, so have some performance to your agent. And it will show that, okay, if I deploy this agent, probably it will solve the problem. Probably it will solve the problem that I set out to solve, right? So just to repeat, I hope you understand the intuition behind reinforcement learning. Then you need to, from the problem statement, right? From our problem statement of reinforcement learning, you have to come up with some interesting idea. Be creative. You can be creative in the agent, and you can like look up what people have done online and pick the best model or some model that is suitable to you. Or you can be creative in the environment setup, because we are not following the landing of the moon of the drone just now, right? We're not telling you to land the drone. So you can be creative in either way. And what would benefit you is first a conceptual model of the problem that you are trying to solve. And you have to program out the agent and the environment. How the environment change as the agent navigate around in that environment. What is the goal that you're trying to set? What is the reward that the environment is giving the agent? And then, yes, show some metrics to show that the agent is doing what it set out to do. And that is all. And do you have any questions? Yeah, I think, yeah, this is a time to, you can start asking questions tomorrow. I will be going through the implementation of the DQN, right? But then to maximize your time, you can already start doing things now and at night, tonight. Yeah, because I think tomorrow can be quite rushed if you wait until tomorrow for me to go through the details, the technical details. Yes, that is all. If you have any questions, then I'll be here. Yes, any question? Or is there any like intuition related question? That is fine as well. Right. I think the common pitfall, right, or one of the confusing thing that I'm also not quite sure when I first started out doing reinforcement learning is how to formulate, right? How do I fit this in? Like, what is the state? Is it a discrete state or a continuous state? What is the action? Is it discrete or continuous? And being discrete or continuous will inform your choice of environment and model representation, right? Why can't we use a lookup table in this cliff example? It is because it's in a cliff. It is discrete. It is a chunk of like square. So you can store them in an array. But if I ask you to, okay, let's make a self-driving car and use reinforcement learning, then you cannot say that, okay, I will steer 45 degree, 45 degree, just 45 degree. That will not work as a car, right? And then maybe machine learning, right? So people will say, okay, so why is machine learning different from reinforcement learning? Like, isn't machine learning used in self-driving car as well? True, but if let's say in this example, you have your object detection. Yes, you can detect the object. You can localize where the person is in the image. But then that is where the machine learning task ends. You take an image, you label a person, that is all. then you will hand over this human location to another module in the autonomous car, right? So it is a separate problem. But in reinforcement learning, looking at the person and behaving in the environment is tightly coupled, right? The agent look at the environment, operate somewhere, the environment gives some feedback, gives some reward, then the agent will respond accordingly. Whereas the machine learning start at the image and as a label or a prediction, more like a prediction. Then you can also say, okay, then why don't we map the image to an action? Because isn't the whole thing of the agent is you get a state and then you output an action? Yes, but because you know that machine learning, you can be overfitting or underfitting, or that it is not always correct, right? There is a probabilistic things to it. So mapping the input to an action directly is not a good thing to do. Or you can only, the machine learning model can only be as good as your training data. Whereas in reinforcement learning, we want the agent to learn something different, right? So reinforcement learning is what is underneath the, if you have heard of DeepMind, AlphaZero, AlphaGo, or the chess or the Go playing board games, right? So those are the reinforcement learning. They are not machine learning, right? Remember, machine learning is only as good as the best data that you lay out in the data set. Whereas reinforcement learning, it will learn and try to improve itself, and then it can come up with very interesting moves that the person cannot even predict. The only thing that we give the reinforcement learning is the goal, right? The reward. It will think that, okay, like if I do this, I'll get better reward, right? The human keep going right, but what if I go left and then I go right? So by exploiting that reward, like the tiny step reward, then it accumulates to a bigger reward and something that is unexpected to a human. Yeah. So those are the differences between machine learning and reinforcement learning. Yes. Right. We still have around 10 more minutes. Anyone has any question, or you can clarify on the problem statement, right? You can also clarify on the reinforcement learning problem statement. Okay, so if no one have any question, then I think that will be it. If you are shy, then I will still be here, okay? If you're shy and you still have question, I will still be here. So thank you for coming. And that is all for the introduction to reinforcement learning workshop.